Hello everyone, my name is Amit Khan. In this presentation I will discuss about system element behavior. So here are the standard test signals in control system. The standard test signals are impulse, step, ramp and parabolic signals. These signals are used to know the performance of the control system using time response of the output. We can see the time response given for each of the signal. For impulse function, we get a when t equals to 0 and we get 0 when t not equals to 0, and its Laplace transform is a. For step function, we get a when t greater than equals to 0 and we get 0 when t less than 0, and the Laplace transform of step function is a by s. For ramp function, we get at when t greater than equals to 0, we get 0 when t less than 0, and the Laplace transform is a by a square. For parabolic function, we get at square divided by 2 when t greater than equals to 0, and we get 0 when t less than 0, and the Laplace transform is a by s cube. The Laplace transform of parabolic function is a by s cube. Next comes poles and zeros. Poles and zeros of the transfer function are the frequencies for which the value of the denominator and numerator of a transfer function becomes 0 respectively. For zeros are the roots of numerator obtained by setting the numerator equals to 0 and solving for s. And poles are the roots of denominator obtained by setting denominator equals to 0 and solving for s. Next we can see the steady state and transient response. We can see the diagram of transient response and steady state response. Basically, when the response of a system is changed from rest or equilibrium, it takes some time to settle down. Now, transient response is the response of the system from rest to steady state. And the response of the system after the transient response is called the steady state response. Now in this diagram you can see the transient response specifications. It is nothing but the time domain representation. Here we can see the transient response and the steady state response. So when the system starts oscillating and then it goes to steady state response. So the time needed to settle down for the system is represented as Ts, that is called settling time. We can see Tp, that is peak time. We can see Tr, that is called rise time. Td equals to delay time, and Np is the peak overshoot. We will define all these variables in our next slide. Here are the transient response specifications. The first one is delay time. And delay time is the time required for the response to reach 50% of its final value in the very first attempt. Then rise time. It is the time required for the response to rise from 0 to 100% of its final value for undamped case and 10 to 90% for overdamped case. Then comes peak time. Peak time is the time required for the response to reach its maximum response or peak overshoot. Then peak overshoot, it is the maximum deviation of the response of the step input. Then comes settling time, it is the time required for the response to reach and finally remain within a specified tolerance band, which is 2 to 5% of its final value. Then comes steady state error. It is defined as the difference between the input and the output of a system in the limit as time goes to infinity. The steady state error will depend on the type of the input, step, ramp, etc., as well as the type of the system, type 0, type 1 or type 2 system. Then comes time constant. Time constant describes the speed with which the measured process variable responds to changes in the controlled output. Now these are some time domain specification and their formula. We can see the formula of delay time, rise time, peak overshoot, settling time. Here is the steady state error for unity feedback system. The block diagram is given. Here the feedback loop is equals to 1, so it is called unity feedback system. The steady state error in terms of GS is ES equals to RS divided by 1 plus GS, and when limit S tends to 0, the steady state error is S into RS divided by 1 plus GS. Here GS is called the forward path transfer function, which is not same as the closed loop transfer function. Now next come damping. Damping is a reduction in the amplitude of an oscillation as a result of energy being drained from the system to overcome frictional or other resistive forces. Here we can see the diagram of an underdamped, statically damped and overdamped system, and how is the response before the system settle down for each cases. So for underdamped system, the system moves quickly to the equilibrium but will oscillate about the equilibrium point as it does so. A critically damped system moves as quickly as possible towards the equilibrium without oscillating about the equilibrium. And for an overdamped system, the system moves very slowly towards the equilibrium. We can define this in terms of damping ratio, that is called zeta. If damping ratio zeta equals to 0, the system is called undamped system. If damping ratio zeta is less than 1, the system is called underdamped system. When damping ratio zeta is equals to 1, the system is called critically damped system, and when damping ratio zeta is greater than 1, the system is called overdamped system. So here how we can calculate steady state error. As we know, steady state error is defined as the difference between the input and the output of a system in the limit as time goes to infinity. Now we will define some error constant. For step input, the error constant is called position error, that is defined as Kp. For ramp input, it is called Kv, which is velocity error constant, and when we give parabolic input to the system, this steady state error constant is called acceleration error constant, which is defined as Ka. As we know that steady state error is dependable on, or it may be defined in terms of the system inputs, what type of inputs we have given to the system, and the type of or order of the system. So here we have defined that we have given different types of input to the systems, and the different errors are called positional error, velocity error, and acceleration error. Here we can see the relationship between input, system type, static error, and steady state error. So when the input is step input, the steady state error formula for type 0 system is 1 by 1 plus kp. For type 1 system, it is infinity. For type 2 system, the static error is infinity. Steady state error is infinity. And we can also see for input, when the type of input is ramp input, the formula of steady state error is kv. For type 0 system, kv equals to 0. For type 1 system, kv equals to constant. For type 2 system, kv equals to infinity. For ramp input or parabolic input, it is ka, steady state error formula. For type 0 system, k equals to 0. For type 1, statistic error constant, k equals to 0. For type 2, the statistic error constant, k equals to constant. This is the response of unit step response of first order system. You can see the response curve, and here CS, that means output, is defined as k by s into ts plus 1. This is the standard form system transfer function response of first order system, where we know gs equals to k by ts plus 1. K is the gain and t is the time constant of the system. Here we can see the response of second order system for unit step input. We have seen this response in the previous slide also. This is also the response of a second order system for unit step input with the corresponding time domain output is given. The formula of the corresponding time domain output is given, that is equals to ct equals to 1 minus 1 divided by root over 1 minus zeta square into e to the power minus zeta omega n t into sine omega dt plus theta, but theta is defined as root over 1 minus zeta square by zeta. And here is the summary of the time constant specifications, time domain specifications, and the formula of maximum percentage overshoot, peak time, delay time, settling time, rise time is given. There is a problem in which we have to determine the delay time, rise time, peak time, settling time. It is given we have to first find the closed loop transfer function of the system, which is cs by rs, that is equals to 1 by s square plus s plus 1. We know that notice that omega n equals to 1 radian per second and zeta equals to 0.5. So we have to find omega d, that is equals to omega n into root over 1 minus zeta square. So we get 0.866. So rise time equals to pi minus beta by omega d. We have to find beta. Beta equals to sine inverse omega t by omega m. So we get beta equals to 1.05 radian. So rise time equals to pi minus 1.05 divided by 0.866, that is equals to 2.41 second. Similarly, we can get peak time by using the formula Tp equals to pi by omega d, and we can get delay time by using the formula Td equals to 1 plus 0.7 into theta divided by omega m. Similarly, we can also get the maximum peak overshoot and settling time by using the corresponding formulas. Here another problem is given. So thank you all for listening.